Next in our journey through the lungs, first the air entered our mouth, our oral cavity, down our pharynx, into the trachea, into the bronchus, and then eventually we're getting into the alveolar. The alveolar ventilation has to deal with essentially the gas exchange. We're starting to get air in the vicinity of the capillaries so that oxygen and CO2 can be exchanged, and we can get oxygenated blood to the heart and deoxygenated blood, removing the CO2 from that and getting that exhaled. But we do have this problem. We have something called dead space. And if we look at our lungs, we have a trachea, and then let's just branch out like this, make it nice and simple. Oop, a little too much on that. Exaggerated. Okay, we got smooth muscle. Control it, bronchodilate, bronchoconstrict. And when we get to, remember these small dots with our capillaries around it, we have air coming in and air coming out. There is approximately 150 milliliters of air that hangs out right in here, and we call that dead space. So as we breathe in, it pushes previous dead space air, pushes that into the lungs, mixes it. Old air comes out, hangs out there, and pushes up there. It's why people who smoke cigarettes, you can still smell the cigarettes on their breath long after they've actually stopped smoking. So this allows for some mixing. This gives us some of the mixture of our actual gases of O2, CO2, and nitrogen. It helps us, as we'll see a little bit later, keep our partial pressures of all these gases very stable. So we can see, if we want to look at the ventilation at the alveolar, we can look at the flow times the tidal volume, but we're going to minus the volume of the dead space. So this equals our same 15 breaths a minute, and then 500 minus 150, and this is going to give us 5.25 liters a minute. So our total ventilation, as we saw before, was 7.5 liters. The actual amount of gas that reaches the alveoli is only 5.25 liters, and this has to do with our dead space. Now that we've talked about how the gas actually gets into the lungs to the alveolar, now we need to understand a little bit about Dalton's law. Dalton's law essentially tells us that our partial pressures, the pressures of all our gases that we are breathing in, can be summed. So total pressure equals, in our case, pressure of nitrogen plus the pressure of O2 plus the pressure of CO2. And we know at 760 millimeters of mercury is sea level atmospheric pressure. We also know that nitrogen accounts for 79% of our atmosphere, O2 21%, and CO2 equals 0.04%. So if you're looking at this from a greenhouse gas standpoint, you can see how any change in the percent of CO2 is going to have a very drastic influence on our atmospheric conditions. Compared to a 1% change in nitrogen or a 1% change in oxygen, it wouldn't be too much, but if we looked at it from that way, that would be a huge difference. However, we are looking at the constant, or basically, if we're looking at all our different pressures, our partial pressures, we need to find out our P total equals 760 millimeters of mercury. So if we know that nitrogen accounts for 79% of that, we can do it this way. Times 0.79 is going to give us 600 millimeters of mercury. The same exercise is going to yield us 160 millimeters of mercury for O2. And then lastly, CO2 is going to be 0.3 millimeters of mercury. Sorry about that. Okay, so you see how all our gases are broken up inside of our system here. Straighten this out just a little bit. And from there we have Dalton's law explaining that the total pressure is the sum of each of the partial pressures. We now know that nitrogen accounts for 600 millimeters of mercury, 160 millimeters of mercury is O2, and CO2 accounts for 0.3. This is going to be very important when for us to understand the gas exchange when we look at inspired air versus expired air.